Hi everyone, welcome to the Tech Colloquium for today. I'm happy the university reopened and happy that Tamash's flight was not that delayed, and so he's still here today. So our speaker is Tutte-Tamas Schwarcz, who is a postdoc at the London School of Economics, working with Ahmed Abdi. So I asked Tamas how to pronounce his name, but didn't ask how to pronounce the name of his PhD university, the Eötvös Loránd University in Budapest.
Eötvös Loránd, yeah.
Thank you. So he works in combinatorial optimization and matroid theory, in particular combinatorial structures like matroid basis families, submodular functions, and clutters. Please.
Thank you. So today I will present some joint work with Kristóf Bérczy, Bogdáka Gehér, András Imele, and László Lovász from Budapest, and Carles Padró from Barcelona. And this is a paper that we presented on this Sunday in Vancouver at the SODA conference. So the title already contains most of the contents. So interaction between skew-representability, tensor products, extension properties, and rank inequalities. For this talk, I will use some other permutations. So I will start with tensor products and rank inequalities, and then representability and extension properties. So let's start with what are these operations, tensor products or matroids. So here, probably most people are familiar with matroids as a pair of a finite ground set and a collection of independent subsets. And in this talk, linear matroids will be important, where the ground set is some finite subset of vectors, and independent sets are linearly independent subsets. You have some graphic matroids, where independence is being a forest. And we will have a particular matroid called the Vámos matroid, which is famous because it is not a linear matroid. So there is no field over which there is a representation. So this is a rank 4 matroid on these eight elements. And the independent sets are the subsets of size at most 4, which are not one of these 5 planes. So compared to the rank 4 uniform matroids on 8 elements, we remove these 5 planes. And we do not remove this 6, C1, C2, D1, D2, otherwise it would be an affine matroid, but it's a basis in this matroid. And the rank function will also be important for this talk. So as probably you know, this is the size of the largest independent set in a subset, and it satisfies some rank axioms like increasing subcardinal submodularity, and they characterize rank functions. So whenever we have a function with these properties, then we can define a matroid. Now for something lesser known, so the main object in this talk is the tensor product operation on matroids. So assume we have 2 matroids on different ground sets S1 and S2 given by their rank function. Then we say that a matroid is their tensor product if it is a matroid on the product of the 2 ground sets, such that the rank of any product set is the product of the 2 ranks. So we have these constraints for the product sets, but no constraint for the other ranks. So it is not a matroid operation in the sense that we didn't fully define it. It is just some property of a matroid that we require to be a tensor product. But the ranks on sets that are not of the form x1 times x2, the rank can be arbitrary. And this is motivated from linear algebra, because if we have 2 matrices over the same field, then we can consider the Kronecker product, and then this matrix represents a tensor product of these matroids. Because this is the Kronecker product is a matrix whose rank is the product of their rank, and more generally, this will be a tensor product, so for any subsets of these ground sets, this will also hold. To get a bit more familiar with tensor products, it is also useful to know that these are the quasi-products where the total rank of the ground set is correct. So quasi-product is just a matroid on a product set, such that if we restrict it to each, assume that the 2 matroids are loopless, then if we restrict it to each row, then we get back the second matroid, and on each column, we get back the first matroid. And for loopless matroid, any tensor product has this property, because in the definition, if we have a single element, then this is just 1. So restricted to a row or a column, we get back the original original rank functions. So each tensor product is a quasi-product, and this satisfies that the total rank is the product of the rank, and this is a characterization of tensor products. As an example, we can consider the rank 2 uniform matrix on 3 elements. Then their unique tensor product is the cographic matrix of K3. So this has 3 times 3 elements, 9 elements, and the edges correspond to pairs. And it can be seen that it's a quasi-product because around each vertex we have 3-element circuit in the cographic matrix. So this will be the U23, and the total rank is 2 times 2. So we have these tensor products, but unfortunately there are some bad news about this operation. So first, this is not a uniquely defined operation, even for linear matrices. If we take different linear representations, then tensor products might be different. And also for linear matrices, there might be nonlinear tensor product. And an even bigger problem is that it's not an operation on all matrices. So this is some part of linear algebra that does not generalize to all matrices. As last Magnus showed, that the Vámos matrix does not have a tensor product with the rank 2 uniform matrix on 3 elements. And this is some nice proof with colorful pictures. So let's see Las Magnus proof why this matrix does not exist. So assume it does. Then it's a matrix on these 3 by 8 elements. And assume it is a tensor product. And then the idea is just to look at these sets in the picture X and Y. And we will compute their ranks and get a contradiction by submodularity. So assume we have this tensor product, then what is the rank of X? And it's not difficult to find these 7 points that will span all of this set X. Because first we can span the first 2 columns, because we have U2 matrix is isomorphic to U23 and the first 2 columns. And then we can span the remaining 3 elements, because here we have 3 planes in the Vámos matrix. And we already included the 3 of the 4 elements, so they will span the 4th. And again, for Y, the situation is the same, just we exchange the rows of A and B, and we find the 7 points that span all this at Y. So we get that the ranks of X and Y are at most 7. And similarly, just by using colors and drawing dots, we can give a lower bound on the rank of the intersection and the union. So if we take the intersection, then we can get a lower bound by adding 1 more point. Because if we add 1 more point to our set, then it will generate the whole ground set by the same argument. So if we add this black point, then first we generate its row, because we have 4 points which are not, which is a basis of the Vámos matrix, and then we generate the last 4 columns, and then generate the rest. So if we add 1 point to X intersection Y, then we generate everything, and the total rank is 8, so the rank of the intersection is at least 7. And for the union, it's easy to see that it generates everything, because we include lots of elements from the second and third row, and then we generate the last 3 columns. So this is a proof that it's not a matrix, because we concluded that there are sets X and Y such that they have rank 7, the intersection also rank 7, but the union have rank 8, and this contradicts submodularity. So this just looks like, first, just some proof for this specific instance of 2 matrices, the U23 and the Vámos matrix. But the reason I told this proof, because we will get some statement on general matrices using no new ideas, just these what we had here. So instead of the Vámos matrix, we can take any matrix and assume that it has a tensor product with U23. And instead of these pairs of elements, we can consider any subsets in this matrix. For the picture, they are a partition of the ground set, but it's not important. They could intersect and not necessarily a partition. And then using the same pictures as before, we can get upper bounds on the ranks of X and Y and lower bounds on the ranks of the intersection and the union. Just we need to do a bit more generally. So previously we spanned here the second and third row by 3 elements. Generally we can span by the rank many elements, these sets. So we take rank A union C and rank A union D elements in the second and third row. Then we span the intersection of x with these rows. Then we span the columns corresponding to A because we have U2, 3. And then we add this many extra elements to span the remainder because we already spanned A union B. Because we already spanned A, so we need just this many elements to span the rest. So now we have some, for this set X of this form, we have some upper bound on the rank now for any matroid which has a tensor product with U2, 3. And the same, we have this for Y as well. And then we can, without any new ideas, we can generalize also the lower bound proof on the rank of the intersection. So instead of sticking to these 7 particular elements, in general, we can say that in the first row, we add the total rank minus the rank of A union B extra elements to span the first row. And then we span the columns corresponding to C union D in the last columns. And then we need rank of S2 minus rank of C union D elements to be added to the second row to span this. And then we span everything. So nothing new happens, just instead of doing just for the Vámos matroid, we can do this with the rank function for any matroid. And then with this many elements, we span the whole ground set, which means that the rank of the intersection plus this new element is at least the total rank, which is just 2 times the rank of the second matroid, because we have a tensor product with U2, 3. So we get some lower bound on the intersection. And for the union, again, we just add some elements to the second and third rows to span these. And then the same way as for the Vámos matroid, we get some upper bound on we get some lower bound on the rank of the union. And then by using submodularity, we got some statement for general matroids that have a tensor product with U2, 3. So this statement now only includes the ranks of this second matroid, and we showed that whenever a matroid has a tensor product with U2, 3, then this inequality is satisfied. And maybe you have already seen this inequality. This is a classical matroid theory result for linear matroid. This is Ingleton's inequality. Ingleton's result states that any rank function of a linear matroid satisfies this inequality, but it's not a consequence of submodularity, so as it is not satisfied by the rank function of the Vámos matroid. For example, in Oxley's book, we have some proof where you need to carefully come up with the statements that you want to use, and then you can prove this in many steps. But in the proof that I just wrote, we were just drawing some colorful dots, and from the Vámos matroid, we could figure out what's happening in general. So this is a new proof of Ingleton's result, and it's more general because it's not just for linear matroids, but for all matroids having a tensor product of U2, 3. And since U2, 3 is a regular matroid, it has a tensor product with all linear matroids, so it is more general. So why is this interesting, Ingleton's inequality? So it is a necessary condition for representability, but unfortunately it is not sufficient. So there has been a lot of effort trying to find more necessary conditions and more linear equalities for the rank functions of linear matroids. For example, using 4 sets, Ingleton's inequality is the only one, which is not a consequence of submodularity. But already with 5 sets, they computed that there are 24 others which are independent and not a consequence of each other or Ingleton's or submodularity. And they also found an infinite sequence of linear rank inequalities. So one can find much more than just Ingleton's. And Ingleton's inequality is an important necessary condition for representable matroids, but it was shown that it is far from being sufficient for representability. It was shown that almost all matroids that satisfy this are not representable. But still, it is interesting that this tensor product proof implies Ingleton's inequality, So we became interested what else does this tensor product approach imply. So in the rest of the talk, that we will study is that whether we can use these tensor products to characterize linear matrices. And secondly, we derived Ingleton's inequality, but that was a known inequality, just a different proof. And another question is whether our method is more general, whether we can derive similar but new statements. And we will answer both questions in this talk affirmatively, at least if we slightly modify it. So for the first question, instead of representability, unfortunately we will need skew-representability. I will explain a bit later. But for the second question, the answer will be simply yes. Our method can give new inequalities that were not known before.
Sorry, can I ask?
Yes?
So does that inequality characterize all matroids that have a tensor product with U2, 3?
No. So actually, yeah, we haven't written a proof, but for example, we checked that, or also these 24 inequalities, all of them are implied by having a tensor product with U2, 3. So it is Ingleton is fair, but probably even these 25 is also not enough. So we don't. So if a matrix has a tensor product with U2, 3, it not just satisfies Ingleton, but it satisfies probably all of these 24 other inequalities that is known on 5 elements, 5 sets. So it is, having a tensor product is much stronger, but we do not know a complete characterization for specifically for U2, 3. So it is stronger than Ingleton. But if we modify a question a bit, then we will see how stronger. Okay, so the general idea is that if a matrix is representable, then it has a tensor product with any regular matrix because we can represent them over the same field. So having a tensor product with any regular matrix is necessary for representability. And this is the statement where we wondered whether maybe this is a characterization of linearity. And first, we notice that unfortunately we have to work with skew fields, also called division rings. These are a generalization of fields where multiplication is not necessarily commutative. And also for these objects, we have a tensor product. So in general, we do not know whether two skew-representable matrices have a tensor product, because in general, this Kronecker product construction does not work, but for a regular matrix, it does work. Here's an example, just to get a bit more familiar with skew-representability. So it is a broader class than representable matrices over a field. For example, we have this non-pappus matrix, where from the pappus configuration, we remove one line. And it is not representable over a field, but it is representable over the quaternions, which form a skew field. So the new question is whether some kind of converse of this observation holds, whether it is true that if a matrix admits a tensor product in a regular matrix, then it is representable over a skew field. And for this question, we have almost yes. So this is our first main theorem, that a matrix is the direct sum of matrices representable over skew fields if and only if this whole sequence of tensor products exists. So we require a tensor product with U2, 3, and then we require such a tensor product which again has a tensor product with U2, 3, and so on. We have this infinite sequence of tensor products that exists. And so unfortunately, this tensor product operation is not associative. That's why it's written like this way. That's one remark. Another remark is that one direction of this theorem is easy. So if we have a skew-representable matrix, then we can have the sequence of tensor products by the linear representations, and then this also holds for direct sums of these matrices, because the direct sums of tensor products will be tensor products of the direct sums. So of course, the difficult direction is that if these tensor products exist, then why are we skew-representable? Another remark is that why is U2, 3 special? And it is special because it has this tensor products. For tensor product, this is the smallest interesting matrix. So if a matrix does not contain U2, 3, then tensor products always exist. They are just adding parallel copies and loops. And if, but for any matrix containing U2, 3 as a minor, we could also use that in the theorem. Because if we have tensor product with such a matrix, then we also have with U2, 3. So this theorem would work with any matrix containing U2, 3 as a minor, but yeah, we stick to U2, 3 because that's the smallest one. And we say a few words about the proof of this, but first let's digest this theorem a bit because it has some consequences that were quite unexpected for us. Because of this undecidability result, that it was shown that skew-representability is undecidable even for connected matrices. So this means that there is no algorithm for the problem, even if we don't care about the running time. And our theorem says that we have some characterization for a matrix to be the direct sum of skew-representable matrices. So if the matrix is connected, then this is a characterization of skew-representability, that these tensor products exist. So we gave a characterization to an undecidable problem, which has some interesting consequences. So first, our result provides some certificate for a matrix being not representable. Because if the matrix is not representable over a skew field, then some member of this sequence doesn't exist, and then this member is a certificate. So if we know that the 13th member of this sequence does not exist, then at least one can check this algorithmically, because the 13th member is just a matrix on n times 3 to the 13th elements. So it won't be a fast algorithm, but it is an algorithm to check all matrices on this ground set and see whether that tensor product exists. So if a matrix is not representable, then our main result says that there is a certificate for it. But this means that since skew-representability is undecidable, this implies that there is no certificate for representability. Because if we could both certify skew-representability and non-skew-representability, then we could also decide skew-representability, because we could check all possible certificates for representability and non-representability. And this is surprising because we would think that we have a certificate for something being representable because we can take the representation itself. But this shows that for skew representability is not the case because we cannot compactly represent skew fields such that we can make the operations in these skew fields and cannot compactly give the skew fields themselves. So this shows that this skew representability is weird, that we cannot give a representation in any meaningful way that would be useful for any algorithm. And another interesting consequence of this result, which we're also surprised by, is that if you would have any bound in this theorem on the length of the sequence that we need to consider, then the problem would be decidable, the representability, because then we would just need to check until that bound the existence of these tensor products. So this means that we do need this infinite sequence here, and not just infinite. There is no computable function which would be enough for giving a bound here. So whatever computable function we take, there exists a matrix such that until that point this sequence exists, but after that point it does not. So that's why we found this theorem interesting, because it has both of these two results, I think, are a bit unintuitive. So hopefully now we are a bit more motivated to see something about the proof of this theorem. So how to prove this? And the most important part of the proof will be just relying on some classical theorem on projective geometries. But let's see what else do we need, and why were extension properties also in the title of the paper. So if you have a matrix and two sets, then let's call this pair modular if we have equality in the submodular inequality. For example, if you have in an affine matrix 2 lines in a plane, then the ranks are 2 plus 2, and the union is 3, and the intersection is 1. And it is a necessary condition, again, for representability, that for any pair there exists a modular extension. By this we mean that if we have two sets which do not yet form modular pair, so we have strict inequality in the submodularity, then this extension says that we have some larger matrix that extends our original matrix and some set Z, such that this Z is spanned by both the original two sets, and if we add Z to these two, then it is a modular pair. So in this example, it says that if we have two lines that do not intersect, then it is possible to extend the matrix such that they will intersect now. And if a matrix is linear, then this property holds, because if we consider the whole vector space, then we have the modularity by the dimension formula. So we can just consider a larger part of the linear space if we have linear matrices. And this is already provides some explanation what happened in the first part of the talk, where we derived Ingleton's inequality, because Ingleton's inequality can be proved using the existence of modular extensions, and our lemma says that having a tensor product with U2 implies the existence of modular extensions. And this is also a main component of the proof of this skew-representable result. So our lemma is that if we have a tensor product with U2 then for any two sets, we can find some modular extension with respect to these two sets inside the tensor product. More precisely, we have some minor of the tensor product, which is modular extension with this definition. And we call a matrix fully modular extendable if we also have any sequence of these extensions. So in a linear matrix, we cannot only just extend it once for two sets, but we can also repeat this. So we extend it for using a pair of sets, and then again we can extend it using another two pair of sets, and so on. So they also satisfy this property that for any sequence of pairs of subsets, we have such an extension where we have modularity. And result independent from the tensor product, but needed for our proof, is that if we have such a matrix, a fully modular extendable matrix, then it is not so difficult to see that then the simplification of the matrix, so we just keep one copy from each parallel class and delete all loops, is some restriction of direct sum of projective spaces. And if we know this, then we can use some classical geometry result that any projective space of dimension at least 3 is representable over some skew field. Because using this geometry result, we have that this fully modular extension property implies that a matrix is the direct sum of rank 3 and skew-representable matrix, because it is the direct sum of some restriction of some projective spaces which are either representable or have rank 3. So we have almost a characterization of skew-representability using this fully modular external property. And we have seen in the previous lemma that having a tensor product is related to these extensions. So if we have a tensor product with U2 then we can do one extension step. So that's where this whole sequence of U2 comes in, that if we have this whole sequence of products with U2 then this will imply that we are fully modular extendable. Because if we multiply it twice, it will guarantee that we can have a modular extension such that again we can have a modular extension, because by our lemma we can find these extensions in the appropriate minors. So our lemma implies that if this sequence in our main theorem exists, then we are fully modular extendable. And then using this first theorem, we get that the matrix is the direct sum of rank 3 and skew-representable matrices. And interestingly, in our main theorem, we can remove this rank 3 case because it also implies without this, because we can apply the statement to the tensor product of n and u to 3, and then conclude that this matrix is the direct sum of rank 3 and skew-representable matrices. But this matrix do not have components of rank 3. So applying to this matrix, we conclude that it is the direct sum of skew-representable matrices, and then this implies that also the original M is the direct sum. So in our theorem, we do not have this exceptional case. That's the high-level idea of the proof of this characterization of skew-representable matrices. Yeah, and the second main result is that if we think back to the Ingleton's inequality proof, we also wondered how general this proof method is that happened there with just drawing the dots and spanning subsets. So we're interested whether we can derive something new easily using tensor products. So let's recall that we've seen that having a tensor product with u2, 3 implies Ingleton's inequality. And so to get something new, first we wondered how previously nonlinear inequalities were derived. And we think that all previously nonlinear inequalities follow from extension properties, like the fully modular extendability that we have seen before. And they even follow from some weaker statement. So there, for extensions, we considered always matrices. But this is a point where it's good to also introduce polymatroid functions. So instead of considering matroid tensor products, it also makes sense to consider tensor products which might be fractional. So by this, I mean that we have some increasing and submodular functions. And for those objects, the tensor product is an increasing submodular function, which again has the correct rank on the product set. But we can also consider this for a matroid rank function, and then we get weaker notions also for this extension property and also for a tensor product that require the existence of some object just fractionally. So not necessarily a matroid, but just some not necessarily integer valued increasing submodular function. So this is for matroids, this fractional modular extendability is a weaker property. It requires the existence of just some not necessarily integral solution. But the non-inequalities, non-linear rank inequalities just used this property. And also, we can slightly generalize our main result, not main result, our first result, that Ingleton's inequality holds. So there, the original assumption was that we have a matroid tensor product with u2, 3. But it is enough to assume that there is a polymatroid tensor product. So for matroids, we have a tensor product which is not a matroid, not necessarily a matroid anymore, just some increasing submodular function which is not necessarily integer valued. And if we allow this fractional solution, then at least it's not surprising that we got some linear inequality, because for fractional solution, some linear equalities describe which have rank functions which have tensor product with some specific matroid like u2, 3. Okay, so back to the original motivation to finding new inequalities. So all previous inequalities follow from this property, that there is this extension. And in particular, this means that previous inequalities do not distinguish non-representable and representable rank 3 matrices. Because if a matrix has rank 3, then it always satisfies this extension property by this picture that I showed before, that if we have 2 lines, then for rank 3 it is true that there is always a matrix in which these 2 lines intersect. So for rank 3 matrix, no previous method gave a new inequality. That's why we were interested in rank 3 matrices, because not all rank 3 matrices are representable. A famous not skew-representable one is the non-Desargues matrix, where we have the Desargues configuration and just remove one line. So by our main result, we know that in the sequence of tensor product, it will stop at some point. So there is no infinite sequence when multiplying with U23. So we started to check this sequence. So first, it turned out that for U23, there is always a tensor product. And because more generally, we could show that for any rank 3 matrix, there exists a tensor product with any uniform matrix, not just U23. And moreover, in the rank 3 case, these tensor products behave nicer. There is a canonical freest tensor product. So there is a tensor product such that if some set is independent in a tensor product, then it is independent in this freest tensor product. So for U23, we had a tensor product. So we started to consider more members of this sequence. And in the end, we could show that there is no tensor product if we multiply it twice by U23, because we observed that it would imply a tensor product with K4. So motivated by our main result, we concluded that it would be interesting to look at this tensor product. And if we have this specific example, that we look at the non-Desargues matrix and K4, that it is not much more difficult to come up with a proof than for this original Las-Wegener proof with the Vámos matrix and U23. So again, in this case, we could found such a proof by giving bounds on ranks and using submajority. So you have some nice combinatorial proof. And why I'm telling this, because this proof method says that if we have such a proof that we have seen, that we can turn it into some inequality that holds for all matrices having a tensor product with, in this case, K4. In particular, it is satisfied for all linear matrix drawing functions. So this example shows that these tensor products are indeed useful. So we can get some new inequalities. And this inequality now looks not so nice. But if we have a proof that the K4 and the non-Desargues matrix do not have a tensor product, we didn't need any new ideas. This just fell out from our approach. So we settled this question that not all linear rank inequalities follow from these extension properties, because for tensor products we could show something more. Yes, so to conclude, I will mention some open problems and finally some motivation why we started this at all. So an open problem is that in the main result with the U23s, we use matrix tensor products, but for these linear rank inequalities, we only use this polymatrix tensor product, so not necessarily integer valued. But it is not clear that for the main result with the sequence of U23s, what happens there if we allow fractional polymatrix tensor products there. So it is, in this sense, these fractional ones are less understood. Another interesting open problem is that for the rank 3 and uniform matrix case, we have shown that there is a unique freest tensor product. And actually, we do not have any example where there is no freest tensor product. So it is a question whether it is true that if a tensor product exists, then there is a canonical freest tensor product. And this question is If true, it would already have application for two uniform matrices. So it's open whether for two uniform matrices they have a freest tensor product. They have a tensor product because they are representable over large enough fields, but we do not know whether there is a freest one. And if there is, it would have some consequences in rigidity theory, where people are interested in rigidity of some graphs, and there are similar maximality conjectures such that the maximal matroid among some matroid family characterizes some notion of rigidity. And the third research direction is that previously people mostly looked at linear matroids over fields, but in this talk we have seen that for some purposes it's better to consider skew linear matroids, so matroids representable over skew fields. And for many algorithms, it's open whether they extend to skew linear matroids. For example, for the matroid matching problem, it's known to be solvable for linear matroid and hard for general matroids, but for this middle ground where we have skew representability, it's open. Of course, our result also provides some negative motivation for this because we have seen that certifying representability is difficult. So it is not clear how useful if we know that matroid is skew representable. But still, it would be interesting to know this. And finally, why did we start to look at these tensor products, and why was also Lovász interested in this question? So originally, we showed another statement that any two matroid admit a coupling, where coupling is something used in probability theory, but one can define it for any set functions. So for matroid rank functions, we say that a matroid is a coupling if it's again on the product of the ground set, and we have these two conditions, that the rank of a set times the whole ground set in the other matroid, and the rank of the whole ground set in the first matroid, and then any set in the second matroid behaves like in the tensor product. So this is some relaxation of the tensor product. But the similar thing for probability measures turned out to be useful. So that is an interesting question whether any two matroids admit at least this operation. And for this it turned out to be yes, so any two matroids at least have this coupling notion. So we started studying tensor products by looking at couplings, and where we were thinking about constructing this coupling that in the end we could for general matroids. And then the final explanation why we started this is because László Lovász and many other people around him are developing this limit theory of matroids. And they have some notions of matroid convergence, but they didn't define a limit object yet. And the idea was that this coupling of two matroids, or more generally of any number of matroids, will be useful because it defines some matroid that contains some other matroid in some sense. And if we do this for a sequence of matroid, then we have some object at least. So that's how originally our work started, but we got quite far from the original motivation of developing the limit theory of matroids. Yeah. So thank you, that's all I wanted to say.
Thank you for the talk. If there's any questions, please wait for the microphone.
So at the beginning, you talked about quasi-products, right? So, I mean, if I take any two matroids and look at their quasi-product, does that give you a matroid? Like, is there a matroid that corresponds to the quasi-product?
Yeah, so any two matroids have a quasi-product. So it's again something that works for all matroids. So for any two matroids, there exists a quasi-product, just not necessarily with this rank. So I think there is always a quasi-product where the rank is the sum of the two ranks minus one.
Is that easy to see? How does that go?
I don't remember exactly the construction, but I think it's not so difficult to construct something where the rank is the sum minus 1. That's the lowest possible rank, but that always exists, yes.
Okay.
Any other questions? I had a question about what you were saying about the certificates about the fields. So is it decidable then if is there a certificate that a matroid is representable, not skew-representable?
Yes, for normal field, the representation is a certificate,
okay.
and it's also decidable. So
Okay.
for normal fields, yeah, representability is decidable.
So then a follow-up, do you think there's an extension of your theorem where instead of U23, that there's representable if there's some tensor product with some other sort of core fundamental matroid?
Yeah, it's a good question. I don't know the answer, whether we can get rid of this skew thing somehow. Yeah, I don't know.
Any other? Well, if there's no other questions, let's thank Tamas again.